All right, hello. Time for another video here. This is 2023. I haven't made a video in a while, but I'm back to making a physics video here for you for a new topic, another new topic that is now required by the state of New Jersey for physics. So it's been a while since I've talked about this, and I'm excited again to now be talking about waves. And there's a picture of waves. We live here near the Jersey Shore, so we know all about waves. But the main concept here is that energy can be transferred in waves. And you know that if you've been down at the beach, because energy, we remember, is the ability to do work. And those waves can do some work on you, especially if you're surfing or body surfing or even just knock you around a little bit. And what a lot of fun to play in the waves, in my opinion, something I've enjoyed. So, yeah, energy can be transferred in waves. That's the first thing that I would have you know about waves. And there's a lot of different types of energy that can be transferred in waves. I'll start off by talking about sound energy and light energy. So, sound and light are two kinds of energy. You know, energy is the ability to do work. So, we'll talk more about sound. And light is the ability to do work too. You know, if you think about it, the transfer of energy is a big part of physics too, right? So we know that light now, in this day and age, can be transferred into electrical energy through photovoltaic cells. So light is a form of energy that gets transferred into electrical energy, and of course, we can do a lot of work with electrical energy. So, and I bring up light, and I also want to mention that it's not just light. There are a lot of things that are on the electromagnetic spectrum, and all these are types of energy that travel in waves. And you're probably familiar with the electromagnetic spectrum before. So this has long wavelength radio waves all the way to very short wavelength gamma rays. So those are the types of electromagnetic radiation. And you can see visible light is in the middle there. And you've heard of the electromagnetic spectrum before, so now you're hearing about it again. All right, so here are the parts of a wave that I would have you know. And the parts of the wave are the wavelength. So that's the distance for one wave to go by. And there's the top of a wave is called the crest of the wave. So a wavelength would be the distance between two crests, as you can see up here in the diagram. That's the crest. And the trough is the low point of the wave. So the wavelength is also between two troughs. Really, if you pick up any place on the wave, then when you get to the point where it repeats itself, that's the wavelength. Amplitude is how high the wave is. That's from the midpoint to the crest, or you could say from the midpoint to the wavelength. So that's the amplitude or the height of the wave. So amplitude is another important word in there. And here they're just saying the origin of the wave, where the wave began. But those are the parts of the wave for you. All right, so waves travel in cycles. And cycles just mean that it's a repetitive motion there, right? So it's a crest, and then it cycles through back to another crest. And then it goes through all its changes, and it cycles through to another crest. So waves travel in cycles is the big deal. And as I said before, the crest of a wave is the high point of the wave, and the trough of the wave is the low point of the wave. And I don't have it written here, but please remember the amplitude is the height of the wave. All right, a wavelength is the distance for one cycle of the wave, and I guess I've already said that in a couple of different ways. So there you go. All right, and yeah, there I give my example as I did before. From trough to trough or crest to crest would be a wavelength. Any wavelength is from where the cycle gets back to where it was when you started looking at it. All right, here's something else I'd like to talk to you about is wave interference. So here they're indicating wave X and wave Y. And this is, you look at the waves and they're pretty much the same, right? So if these waves meet each other and they're lined up this way, there's a result of those two waves. And that becomes a bigger wave that is made because of interference that they call constructive interference. Both of these waves are kind of lined up. So when they are meeting each other, the crests meet each other and they build each other up again. And if you ever seen that, sometimes it's like a wave going back out again, but like the waves hit each other and sometimes it like jumps up again because it's the same kind of effect there, but it happens for all kinds of waves. We usually talk about interference as being a bad thing, like interference in football, or you're interfering with what I'm trying to do. But here in this physics terminology, this can be considered somewhat positive, right? Constructive interference. And here's destructive interference, where in the second one on the right-hand side here, right? The trough is lined up with the crest. So what happens is they cancel each other out. I don't know if you've ever seen that. Like sometimes I'm at the beach and like a wave is coming in, but there's also the tide rolling out. And sometimes the tide rolling out cuts the wave, so it looks like it's going to be a big wave, and then suddenly it kind of drops out. And that's called destructive interference. So there you go. All right, so constructive interference, what you would say is the waves are in phase. And if they're out of phase, that would be destructive interference. So if they're in phase, the two waves are both cresting at the same time. All right, so another terminology here, frequency. That's the time it takes for a wave to go through one cycle. And for frequency, we measure it in hertz. And we're very familiar nowadays with the increasing speed of computers, and they measure them in hertz. I remember when the number was very low, and now it's very, very large. The computers are becoming more powerful. And what it's doing is it's cycling all that information around that digital pathway. And it happens so fast now that these calculations can be made that are incredible. So you've heard hertz involved with computers before. All right, so frequency in hertz would be the number of waves per second. How many waves per second am I dealing with here? That's the frequency in hertz. And wavelength is the number of meters per wave, right? The length of the wave, meters per every wave. So the symbol for wavelength is called lambda, and it's a Greek letter. We're running out of regular letters for our formula sheet. We got to add in Greek letters over here, right? Look at that. All right, so why I'm telling you this is because think about this for a minute. The speed of a wave, how fast is the wave moving? Well, that's the frequency multiplied by the wavelength. Here, I'll show you what I mean. There's my formula. There's the newest formula for you. Doesn't even have a real letter in it, right? It's got this lambda. But speed of a wave is the frequency multiplied by the wavelength. And it should make some sense, right? Frequency is waves per second, right? So there's your frequency, waves per second. And there's your wavelength, meters per wave. So, of course, the waves unit cancels out, and you're left with meters per second. And you're familiar with meters per second being the unit for speed. So we're right back to it. And now we've tied in waves into what we did right from the beginning, that idea of speed. That was the first thing we did on day one, right? Now we're talking about the speed of waves. And they can move fast. Everything on the electromagnetic spectrum moves at the speed of light. Everything on the electromagnetic spectrum moves at the speed of light. And the speed of light is 3 times 10 to the 8th meters per second. And the letter C is used to symbolize that. And many of us are familiar, right, with the equation E is equal to mc squared. Who do you think of when I say that? Albert Einstein, maybe? That's his famous equation. What he figured out is mass is energy. The m is our old mass. And if you multiplied mass by the speed of light, that tells you how much energy you have. Now, it takes a lot to break down mass for some types of mass, so it's hard to get at that energy. But this is the whole idea of nuclear energy, right? If you can break that down, you release amazing amounts of energy. Albert Einstein figured that out. And it actually tortured him later in life because he realized that this was helping to create the atomic bomb. And he petitioned Roosevelt, President Roosevelt, during World War II, and he said, you better get in there and start making an atomic bomb because I know the Germans are going after it. And if they get there first, it could be a very different world. And there were scientists over in Germany working on that. And Einstein, lobbied FDR, Franklin Delano Roosevelt, and we got there first. And but he was, he wanted us to get there first because he saw the Germans as a big threat. But he was also had very mixed feelings and bad feelings, I guess, or guilt a little bit about unleashing this kind of thing on the world. He was just looking for new information. But by the way, he's also the person who figured out that photovoltaic effect. He got a Nobel Prize for that, and that's the whole solar panels. So, Mr. Einstein, you did all right for us, in my opinion. You had your thought process there. By the way, because Einstein did that, Hitler put a bounty on Einstein's head. And so he wanted Einstein dead, and he would have paid money to kill Albert Einstein. And that never happened, and Hitler ended up killing himself in a bunker as the end of the war was happening. And that's what history says. And Albert Einstein died of old age in Princeton, New Jersey, if you didn't know that. All right, so there's a little bit with the speed of light and all these kind of things. All right, so as I said before, all of the waves on the electromagnetic spectrum travel at the speed of light. All right, so let's do an example here, right? Blue light has a wavelength of 400 times 10 to the negative ninth meters, nanometers, but there we go. There's our scientific notation, a very small number. So what is the frequency of blue light? Well, how would you go about solving this? If you want to, you could give it a try and then pause, give it a try, and come back and see how you did. That would be a good challenge for yourself. All right, did you do it? Are you back now? All right, here's how I solve this problem. I identify the information. There's the speed, the 3 times 10 to the 8th meters per second. There's the wavelength, 400 times 10 to the negative ninth. And I'm looking for the frequency. So speed is frequency multiplied by wavelength. So 3 times 10 to the 8th is equal to frequency multiplied by 400 times 10 to the negative ninth. So I divide off the 400 times 10 to the negative ninth, and I get a frequency of 750 times 10 to the 12th hertz, or 7.5 times 10 to the 14th hertz, or 750 with 12 more zeros after it. Anyway, you cut it, there's the solution, and now you're probably ready to practice problems involving this equation, this brand new equation. So if you have any questions, bring them back to class with you. I'll be around for this year, and we'll talk about it. All right, see you next time. Bye for now.